Excellent. So today I have a real pleasure in introducing Terry Hughes, who's the Director of the Centre of Excellence for Coral Reef Studies at JCU. He's probably one of the most well-known and distinguished coral reef scientists in the world. It's a very big reputation, and a lot of his work over the years is really focused on, or are sort of a recurring theme. He's done a lot of things. He was involved in the Safe Operating Space for Humanity work, involved in lots of things, but there's been a sort of a common theme through it, really around kind of looking at the application of new knowledge for the management of marine systems. You know, as part of his long career, he's received a number of awards. He's been, in 2006, he was voted one of the 10 most influential people by Nature magazine for that year for his work on coral bleaching and climate change. He recently received the Einstein Professorship for the Chinese Academy of Science. He's also won the Darwin Medal from the International Coral Reef Society, Eureka Sherman Award, and a bunch of other awards. I think I've conveyed enough the fact that he's very highly respected. He's also a member of the Australian Academy of Science. He's also been a laureate fellowship, held a laureate fellowship and also a Federation fellowship as well. And he's going to talk today about global warming and coral reefs, and I think you're going to really enjoy it because it's a particularly important topic and something as Australians and New Zealanders we feel particularly passionate about. Thank you.
Good morning, everyone. Thanks for getting out of bed early. It's a great pleasure to be here, and I'd like to thank the organisers for inviting me, and I guess thinking outside of the box a little bit. I'm a biologist by training, and I rely on my collaborators who did physics and maths rather than biology for their expertise in climate and so on. So thanks for inviting me. I'm going to talk today not so much about the climate as the impact of the climate on ecosystems. And my favorite ecosystem that I've studied for a long time is coral reefs. Coral reefs are important to mostly small, poor developing countries. They provide livelihoods and food security to about 200 million people throughout the tropics. So global warming and its effects on reefs and on tropical coastal societies is a big issue. My clicker doesn't work. Hopefully it'll work next. So there are a number of elements of climate change that impact on coral reefs. It's pretty clear from the recent global coral bleaching event, which I'll describe in a moment, that global warming and heat waves is the #1 contemporary rather than future threat to coral reefs. And the scale of it, as I'll show you in a moment, is quite astonishing. More locally, we're also seeing impacts of weather extremes, including floods and cyclones. Sea level is not a major issue for coral reefs. It's much more important for human coastal societies. Coral reefs dealt with over 120 meters of rise in sea level at the end of the last ice age pretty handily, so another meter or so is not going to bother them. And finally, ocean acidification is a longer term problem for reefs, and it's becoming clearer with the events of the last 2 years that corals are likely to cook under a business as usual emissions trajectory long before ocean acidification becomes a major problem in the tropics. What I just said is heresy among many of my coral reef friends who work on ocean acidification, but I'm prepared to argue that point. I'm having trouble with this clicker. I'll just use the computer bar, sorry. I want to show you a small movie. Can somebody give me a hand with this, please? Can you get that to work? Am I hitting it the wrong way or something?
Should be right. Go ahead.
That's forward, right? Yeah, that should have come on automatically. Is there a click thing on there somewhere? Click. All right, I'm sorry. I had a movie there that doesn't appear to want to work. It worked in the green room. Yeah. Won't work? Oh, well, never mind. What you've just not seen is a spectacular underwater movie of coral bleaching. So you'll have to take my word for it. Sorry about that. That means another movie later on won't work either. So today I'm going to talk about heat exposure as a driver of bleaching. While the movie was running, I should have explained what coral bleaching is. Bleaching is a stress response by the corals. They turn white. Corals get most of their color from microscopic algae that live in their tissue, and the heat can kill those algae, causing the coral to turn white. If bleaching is extreme, then many of the bleached corals will die, and over the last 2 years, we've seen close to 50% of the corals on the Great Barrier Reef die because of back-to-back bleaching. I'll talk in a moment about global patterns of recurrent bleaching. Then I'll talk about the Barrier Reef. And finally, I'll talk about prospects for recovery of the Great Barrier Reef. So this first graph comes from a paper we published in Science 3 or 4 weeks ago. This analysis was done by Janice Locke at AMOS, who many of you may know. It shows temperature anomalies through time from 1870 up to the present. The color of the dots in that graph represent different phases of ENSO cycles. So the red dots, for example, are El Nino periods. The blue are La Nina, and the black are ENSO neutral years. What it shows is that temperatures are rising, surprise, surprise, throughout all phases of ENSO cycles. And if you look at the final part of that trajectory, what that graph says is that sea temperatures in the tropics, so these are data for 1 degree pixels throughout the tropics where the pixels contain a coral reef. What it says is that sea surface temperatures in the tropics today during La Nina periods are actually warmer than they were during El Nino periods 30 or 40 years ago. So we often hear people, mainly climate skeptics, saying that coral bleaching is a natural event caused by El Ninos, which are a natural recurring cycle. That's not true. We have seen many El Ninos over recent centuries with no bleaching. The first time the Great Barrier Reef bleached was in 1998. Yes, that was an El Nino period, but we've had 2 more recent bleachings that were not during El Nino periods. And globally, we're seeing more and more coral bleaching throughout ENSO cycles, which will lead in about 50 years' time to annual bleaching in most parts of the world. So this is a map of the world showing the most recent global bleaching event. So red is severe bleaching, orange is less severe bleaching, and the remaining color, blue, is no bleaching. So there are 100 dots on that map. So this paper, which we published a couple of weeks ago, analyzes the bleaching record at those 100 locations back through time for about 4 decades, back to 1980. So when I was a PhD student, sometime in the late Pleistocene, bleaching was unheard of. I first encountered bleaching in the Caribbean in 1987. And as I said, the first bleaching event in this part of the world, on the Great Barrier Reef, was in 1998. So bleaching is a relatively modern phenomenon. So this bar graph shows the number of those 100 locations that have bleached either severely or moderately and through time. So the big peak in 1998 is very conspicuous. 2010 is also considered to be a global coral bleaching event, and the most recent one was in the 2015-2016 El Nino period, where Northern Hemisphere reefs bleached in the summer of 2015, and in the Southern Hemisphere we saw severe bleaching on the Great Barrier Reef early in 2016. This is a graph taken from that data. So the two trajectories on the left coming down in black and blue are the number of those 100 locations that remain unbleached through time. Now that's important because of the concept of spatial refuges, special places that don't bleach, which conservation biologists often seek out as a place to protect. And what this graph shows is that the world is littered with former potential spatial refuges. So only 6 out of those 100 locations have not yet severely bleached, and even they have bleached repeatedly less severely since 1980. And the two trajectories on the right show the accumulating number of bleaching events at those 100 locations. So in total, on average, each of those locations has seen 6 bleaching, of which half, so 3 per location, have been severe. So the return time between pairs of recurrent bleaching events has shrunk consistently from one decade to the next. In the 1980s, it was about 25 years between a bleaching event then and the next one. Now the median gap between recurrent bleaching events since 2010 is 5.9 years at the scale of those, each of those 100 locations. And that's a big concern because of the time it takes for a heavily damaged reef to recover. It takes about 10 to 15 years for the fastest growing corals to replace themselves if they've been badly damaged. So as bleaching has become more and more the new norm, we see the development of these predictive tools or forecasting tools for bleaching. So this was BOM's outlook for early 2016, and you can see that there were very extreme temperature anomalies throughout the Great Barrier Reef in the summer of 2016. Here's another example from Noaa. This is NOAA's Coral Watch program, where again they're predicting very high temperature anomalies along the east coast of Australia. That one is for early 2017. So for the last 2 summers, we've seen extreme temperatures on the Great Barrier Reef, which caused coral bleaching. So the Barrier Reef has now bleached 4 times. 1998 was the first, and a huge surprise. We were unlucky to have a second bleaching event only 4 years later, unlucky for that period. And then we were lucky to have a 14-year gap between 2002 and 2016. And now, tragically, we've seen the first back-to-back bleaching. So I led a very large team of researchers to try and learn as much as we could from the 2016 and then the 2017 bleaching event. So the most basic preliminary research question is, where's the bleaching happening and how severe is it? That then leads to other more interesting questions like, can we explain the geography of the bleaching and what effect is it having on the ecosystem? So the red squiggles on the map show the flight paths that I took with my research assistant in that little chopper, which we spent 3 days in, and in another 5 days in fixed-wing aircraft. It looks like the pilot had 1 gin and tonic too many, but the purpose of those crazy flight paths was to try and intercept as many reefs as we could. We got to about 1 out of every 3 of the reefs that make up the Great Barrier Reef, and we scored the amount of bleaching that we saw. We also did a huge amount of work underwater. and I'll only describe a very small amount of that very briefly. This slide shows the ground truthing of the aerial bleaching scores, and to make a long story short, by going underwater at each of those red dots, we could show that the aerial bleaching score for those reefs was actually incredibly accurate. This slide is an insurance slide in case the following movie doesn't work, and it doesn't look like it will. So the point of this slide and the movie is that aerial surveys of bleaching are quite easy to do because it's so conspicuous. So that reef literally looks snow white from the air. That would be category 4 bleaching, where more than 40% of the corals are bleached. And the movie's working. Ah. Okay, this runs for about 30 seconds or so. This is taken from the helicopter north of Port Douglas. And you can see the whiteness of the corals. The yellow blotches there are soft corals, which also bleached. So all of these are very severely bleached reefs. And in 2016, for 3 days of flying north of Cairns, that's all we saw. Severely bleached reefs for a distance of about 700 kilometers from Cairns all the way up to the maritime border with Papua New Guinea. Okay, I'm glad one of the movies worked. So these are the results. The top 3 maps show the bleaching patterns done from aerial scores in 98, 2002, and now 2016. So red is severe bleaching, where more than 60% of the corals are bleached. So the footprint in the top 3 maps is different in each event, which means that the cumulative footprint is much larger than each individual bleaching event. And the bottom 3 maps show where the heat was for longest. So the metric here is degree heating weeks, which I'm sure most of you are familiar with. It's the degrees in centigrade above the long-term summer maximum multiplied by the duration in weeks, although people also talk about degree heating days or degree heating months. So the bottom 3 maps are heat maps, no pun intended, of where the degree heating weeks were high or low. So blue is 0, no heating. So the north in the first 2 events in 98 and 2002 had little or no heating and little or no bleaching. So until 2016, we thought that the Northern Barrier Reef was one of those special places that was a spatial refuge from bleaching. Sadly, that turned out to be completely untrue. So clearly the different footprints can be explained very well by where the heat was and where it lasted for longest. We went back to all of our reefs underwater 8 months later to see what was left, because the ultimate losers in a bleaching event are not the corals that bleach versus don't bleach, it's the corals that survive versus die. So we went back to measure who died and by how much, and how that related to the pattern of heat. So these are the reefs that we visited twice, at the peak of the bleaching and again 8 months later. And the color code shows the amount of mortality. So north of Cairns, most of the reefs either had 50 to 75% loss of corals or higher, 75 to 100. We were able to use that data in combination with our aerial scores to come up with a calibration curve that allowed us to convert our 1,156 aerial scores into mortality scores, and then we could do a heat map of mortality with a pretty good spatial resolution. So the right graph is the thermal footprint again, and the left is the pattern of mortality. So red is 50% or more mortality. So the northern third of the Great Barrier Reef, from Cairns northwards, suffered a huge mortality event in 2016, far greater than any cyclone. In fact, the comparison I've made is that it's as if 10 Category 5 cyclones have walked ashore between Cairns and New Guinea holding hands in terms of the scale of that damage. And that's significant because everything we know about the recovery of reefs is after cyclones, but the processes involved in recovery from an event of this scale will be quite different, I think. This is a graph of the change in coral cover on those reefs over an 8-month period, plotted against the degree heat exposure that each of those reefs experience. The y-axis is on a log scale. So what this says is if there's no heat stress, then there's no loss. In fact, the southern reefs showed a small increase in the abundance of corals. By the time you get to 4-degree heating weeks, the average decline on that curvy regression line was 45%. And by the time we got to an exposure of 8 or more, we're looking at 60 to 90% mortality. 29% of the reefs on the Great Barrier Reef were exposed to 6-degree heating weeks or higher in the summer of 2016. An important part of this story is who died, and I haven't time to go into that in any great length. But bleaching is incredibly selective. In particular, the most susceptible corals are branching corals and table corals that look like a coffee table on a stalk. Those corals are important functionally for a reef because they provide most of the three-dimensionality, the nooks and crannies that are important as a fish nursery and for all the other creatures that live on a coral reef. The more resistant ones, which are sometimes called winners, are the thermally tolerant ones, like the coral on the right. That's a Porites coral. They're very slow growing, and they're tough. They live a long time. They're resistant to crown-of-thorns starfish, to cyclones. They don't mind high amounts of sediment, and they tend not to bleach, or if they do, like this one, they generally regain their color in the ensuing cooler months, and they survive. So what we're seeing on the Great Barrier Reef and on reefs worldwide for the last 30 years now is a quite dramatic shift in the mix of species. That's potentially a source of resilience for coral reefs moving into the future. Tragically, in 2017, we saw another bleaching event occurring on the Great Barrier Reef, and the footprint of it, which we still haven't quite published, is different again. So the 2016 event was very much a northern affair. In 2017, the reefs that were severely bleached occurred in the middle of the reef. So the cumulative impact of that back-to-back event is actually now fully 2/3 of the Great Barrier Reef, with the south escaping in both of those two events. I haven't time to talk about it today, but the response of the corals in 2017 was actually quite different from 2016. And because of the proximity in time of those two back-to-back events, the outcome of the 2017 event is actually partially dependent on what happened in 2016. There's a contingency happening. So the reefs in the north didn't bleach as much as 2017, even though they were actually hotter in 2017. And that's because the heat-sensitive species have largely been removed by the earlier bleaching event. So the survivors that made it through the 2016 event that bleached mildly and regained their color, bleached mildly again in 2017. So despite 2017 actually having a higher degree heating week metric for almost all of the Great Barrier Reef compared to the year earlier, the bleaching was less severe. We should have seen bleaching in the south in 2017, given the level of elevated heat we saw there. But again, it seems like the prior mild exposure that the south had 1 year earlier has toughened the corals up, so they bleached less than we expected. And finally, in the middle, we saw more bleaching in 2017 than we expected. taking into account the heat exposure in 2017. And we think the reason there is that the moderately bleached event in the middle of the reef in 2016 injured and fragmented and weakened the corals physiologically so that they bleach more readily in the middle in the second year event. Anyway, that's quite complicated. I hope you followed it. The main point is that we're now seeing interactions between these recurrent events. So instead of them being discrete, well-spaced events, we're now starting to study them as sequences of interactive events, where there's not only a cumulative effect, but an interactive effect between multiple bleaching episodes. So I've talked about the first 3 items. I'm going to wrap up now and talk about the prospects for recovery. So I've mentioned the concept of spatial refuges a few times during the talk. This is a cumulative map of severe bleaching throughout the 4 events on the Great Barrier Reef, and the question mark illustrates 2 regions, a small northern one and a slightly larger southern one, where we haven't yet seen severe bleaching. We've seen moderate or minor bleaching in 1 or more of those 4 events, but not severe bleaching. So these are potential candidates for being spatial refuges. The north has some hydrodynamic features, high currents across the Torres Strait and upwelling at the edge of the continental shelf, which may afford it some protection. The southern reefs, which are the Swains group of reefs, I think it's sheer dumb luck that they haven't bleached severely yet, and it's likely that they will. Those reefs are now also dealing with an outbreak of crown of thorns starfish. Another issue is the connectivity of those reefs. How connected are they? Can larvae move from those 2 question marks and repopulate the depleted coral populations in the rest of the Great Barrier Reef? And again, that doesn't seem very likely, because the East Australia current comes barreling down past the southern question mark, and a gyre in the Gulf of Papua seems unlikely to transport the northern refuge larvae further south. So our research now is looking at hydrodynamic modeling and larval dispersal of corals to look at the prospects for recovery, and we're also directly measuring stock recruitment relationships, which I'll explain in a second, at the scale of the Great Barrier Reef. So we know quite a lot about patterns of replenishment by corals at the scale of the reef. The map on the left is from a paper I published in Nature in 1999, and the graph on the right it shows the relationship between the abundance of corals on a reef. Each of those black dots is an individual reef on the map, and the amount of recruitment that we measured on each of those reefs. So what the graph shows is a nonlinear relationship between the stock size and the production of larvae versus the amount of larvae that each reef experiences. It's nonlinear, which is important. What the graph says is if you go from a reef with lots of corals, 100% cover, down towards 0, you get a disproportionate decline in the amount of recruitment that reef receives. So for many of the important species, the table corals and the staghorn corals, we have seen a decline of 75, 80, 90% on many of those reefs. And so the expectation is the recruitment onto those reefs now, compared to our historical measurements of recruitment, will be very substantially diminished. Sorry, wrong way. So this is 2 photographs showing the recruitment tiles that we deploy. The picture on the left is from 2004. So we've done these barrier reef scale deployments of recruitment patterns several times before the bleaching. You'll notice in the before photograph, the tile is surrounded by lots of adult healthy corals that are producing lots of coral babies. And the picture on the right was taken in November last year when we deployed these tiles. We retrieved them 2 weeks ago. And it shows a typical reef north of Cairns where most of the adult coral is in shallow waters now dead. So the question is, where are these larvae going to come from, and how many of them will there be on those recruitment panels? So we put out 600 panels just before the last annual spawning. We've just retrieved them, and we're now counting them. We have counted the Torres Strait tiles. That's 100 tiles so far. And I can tell you that the amount of recruitment on the tiles today is 4% in that region compared to previous times when we've done it. Our expectation is that the southern third of the Great Barrier Reef will still have very high levels of recruitment. And I don't know yet whether there's, because we haven't counted them, whether there's any evidence that that southern production of baby corals is being transported northwards against the East Australia current to bolster recruitment in the region between the Torres Strait and the southern end of the Great Barrier Reef. Stay tuned. So to sum all that up, I've shown you that recurrent bleaching is the new normal. We've gone from an era before the early 1980s when large-scale bleaching simply didn't occur, to a transitionary period in the 80s and 90s when El Niños became dangerous for coral reefs, to the current period where we're seeing more and more bleaching throughout ENSO cycles, including the back-to-back bleaching that we've just seen in 2017 on the Great Barrier Reef. I've shown you unprecedented mortality has now occurred in shallow corals on fully 2/3 of the Great Barrier Reef. The Great Barrier Reef today is a greatly diminished place compared to just 2 years ago. I've also argued that the recovery time for corals, 10 to 15 years for the fastest growing species, is longer than the return time for these bleaching events, and that's going to become more and more of an issue in the future. The north and central regions are changed forever, and I think our recruitment study will give us a better handle on the length of a recovery to a new system with a different mix of species that's likely to unfold over the next 10 to 20 years or so. But we have a glass half full, half empty scenario on the Great Barrier Reef. If 51% of the corals died north of Cairns, that means 49% of them survived. It's about 1 billion corals, and they probably produced trillions of larvae in the last annual spawning event, and we'll soon see how many of them settle onto the reefs throughout the Barrier Reef. Thanks very much.
Thanks very much, Terry. That was excellent. We have some time for some questions. Do we have any questions in the audience? Mary?
Thank you. Amazing talk. Thanks very much. And this is not a scientific question. My question, well, in some senses it is. What percentage of our federal politicians have seen your movie of flying over the reef?
I'm not sure.
Any?
We put that movie, the aerial one that actually worked, on YouTube a few days after we finished the aerial scores, and 5 million people watched it in the first 4 days. So it's out there. It was a huge media story, and it's a recurrent media story, not just in Australia, but globally. I've talked to many politicians, formally and informally. I've taken some of them snorkeling on the reef, and I think most of them get it. They don't necessarily admit it, depending on which side of politics they're on. So you've touched on the politics of the barrier reef bleaching, and it's something that the people involved in the science are very much aware of. It's always struck me as ironic, I said this last night at the public forum, that Australia has responsibility for stewardship of the Great Barrier Reef, but we're also the world's largest exporter of coal and soon fracked coal seam gas. And that industry just has to transition to renewable energy as soon as possible, or we won't have a Great Barrier Reef in 50 years.
Terry, I have a comment and a question. So the comment is, firstly, thank you on behalf of my children and my grandchildren for fighting so hard for trying to protect the Great Barrier Reef. I know it's not always easy. I know it's not always easy being in the public spotlight, facing controversy, ignorance, prejudice, and outright aggression. So thank you. I know there's a personal cost associated with that. The question is, so some of the corals are very sensitive. Is there anything that can be done to speed up their evolution to be able to deal with the warming waters, even if we meet the Paris goals?
Yeah, so you're referring to what some people call assisted evolution, and a related issue is assisted migration, where you pick things up and move them. I have to admit I'm a bit skeptical about that approach, and the reason is I look at the numbers and I'll think of population genetics parameters and models. So there's 1 billion or more corals that survived. They're tougher on average than the billion or so that just died. The mix of species has changed, but within individual species, the mix of genotypes has changed. So the Great Barrier Reef has just gone through one hell of a natural experiment, a natural selection event. And it seems very unlikely to me that you could artificially breed in a laboratory, in an aquarium, enough larvae or enough adult corals to change the gene pool of common species of corals that have a surviving population in the tens to hundreds of millions of individuals. It just seems to me like the inoculum would be always tiny compared to a rapidly evolving wild population. And I don't think it would make much difference. And there are lots of examples around the world of people trying to use artificially bred seedlings to restore adult populations. A good example is the Australian chestnut, where several 100 million trees died. There are genetically modified seedlings of that species in greenhouses around the United States. But how do you plant 250 million of them and wait 100 years for them to replace the adult population? There's a mismatch in scales, I think. The other issue is assisted migration, where you move corals from one place to the next. Well, corals are already on the move, and we've seen this through geological history. So the tropics are expanding. We're seeing corals moving south along the east and west coast of Australia and along the east coast of North America, along the Ryukyus chain in Japan, as the subtropics become warmer. Again, we're talking about billions of larvae, and I don't think we as humans can compete with that.
Carl Mallon, I think I read some rather colourful language being used about some of your work a few weeks ago from the Tourist Association, and it seemed to me that it was shooting the messenger regarding, I think, the threats to tourism, where they were saying, well, you know, the work on coral reefs is just deterring tourists from coming to see the Great Barrier Reef, which I thought was sort of odd in some ways, because one, you're the messenger, but also it seemed that they should be leaping to the fore to try and defend the reef rather than criticise the scientists who are reviewing that. I mean, I guess that's where you live and breathe in amongst the same community. What do you think some of the learnings in terms of trying to bring, for example, the tourist sector to the fore in terms of supporting your science and I guess trying to bring politicians, etc., on board with the assertions that you're making about the solutions we need?
Okay, thank you. There's about 19 parts to that question. So firstly, let me point out the tourist numbers on the Great Barrier Reef have increased every year for the last 5. And people are using terminology like last chance tourism to describe that phenomenon. So the tourist numbers are not going down. Secondly, the tourism industry is incredibly concerned about this bleaching event, particularly now that it's happened twice in 2 consecutive years. Thirdly, there's no single voice for the tourism industry. And I had many emails after this particular individual called me a dick, which was published by the Guardian, thank you, encouraging me to keep speaking out. In 2016, after the first bleaching event, 140 tourist operators wrote to our Prime Minister and said, bleaching is a threat to our industry, which employs 70,000 people and is worth $6 billion a year. What are you going to do about the Adani coal mine and Australia's energy policies? So there's no single voice or single opinion for the Great Barrier Reef, and that particular individual has his opinion, he's entitled to it, but it's not a majority opinion from where I'm seeing.
We have time for one more question. Okay, gentlemen.
Sorry, you sat down there and you're nice and cozy. Sorry, last question. Terry, what are the chances of severe bleaching happening again this year?
Well, we've been looking very closely at the forecasts from BOM and Noaa. We also have underwater temperature sensors and in situ observations. It looks unlikely, is the bottom line. So the temperature currently is just very slightly above the long-term average, which means it's significantly cooler compared to the start of summer last year and the year before. And it's expected to, the anomaly is expected to diminish through March and April as the weak La Nina kicks in and we get a bit of rain in the tropics. So it's looking good for this year.
Thank you very much. Okay. Please join me in thanking Terry for an excellent speech.